Carbocations that contain a trivalent positively charged carbon atom react with water to give alcohols. Okay, so that's this reaction here. How can you account for the fact that the following carbocation, this one, gives a mixture of two alcohols on reaction with water? Okay, so let's look at that. So this, and I will write this here, CH3, CH3. This carbocation here, it reacts with water, and the reaction with water is, we can actually draw curved arrows that show this. So again, the curved arrows, as we've discussed, begin at the site of electron density, that's the tail, and then end, the head, is where the electrons are going. And in this case, we have a new compound here, or this is actually an intermediate, which means that it's not isolated because we have to do something first to this intermediate, and that is, we just treat it with a mild base. So let's just, and usually in practice, this is something like sodium bicarbonate, and we will draw the curved arrows this way, and that will give us our alcohol. And I'll put the alcohol here. CH3, CH3. Okay, that is the compound that we're looking at here in the first part. Now the second part says that there are two different alcohols being produced, and notice that we're starting with this compound here, CH2, that has a double bond next to the carbocation. So here's the carbocation, there's a double bond. Now, if we react this one with water, we get the alcohol that we see first here. So that gives us product 1 right here. But notice that since we have a double bond next to the carbocation, we can draw a resonance structure in which I'll use a different colored arrow, different color of arrow here. We can draw the electrons there, and I'll draw a resonance arrow here to show that we have resonance putting the positive charge on that end carbon, and here we have two resonance structures, and notice what this indicates is that this carbocation actually has a carbocation character at two different carbons, this one and this one. And let's just erase that. And it also means that a water molecule can react at either of those positions. And if it reacts here, on this end, we end up with the product shown here. Because the water attacks, we get this OH2 intermediate, and then the base pulls off the proton, and we end up with this product here. So both of these products come about because of addition of water to both of these carbons, each of which is a sort of half of a carbocation in the resonance hybrid, and we can draw the two resonance structures indicating that there's a full positive charge on each of these, but since it's two resonance structures contributing, essentially the real molecule has half of a charge, so we can draw kind of this resonance picture here where we have our methyl there, and we have, so this is the compound And the resonance here puts our double bond there. So that's what we're looking at. And then you see this sometimes where you have a dotted line and a positive charge in the middle, or you can show that you have delta plus here, delta plus there, and a dotted line. But these are not ideal ways of representing what is essentially a hybrid of two resonance structures.